Good afternoon. Welcome back to the course of computational method optimization. And this course we will talk about the Armijol search. And in last class we have discussed a method for solving this unconstrained optimization problem, which is the gradient descent method with constant step size. The scheme is like this. If you have a point xk, and then you choose a direction which is a negative gradient, and then you choose a constant step size. Actually, this method is quite simple, okay, because you do not need to change the step size in each iteration. And this method converges only when the objective function is L smooth, okay, which means your gradient is L ellipsis continuous. And we can choose the step size alpha k equal to alpha, which greater than 0 or less than or equal to 1 over L. Actually, in some materials, you can see they can also choose 0 to 2 over L. Actually, if you choose this, you cannot have the equality here, okay? But if you choose 1 over L, you can use the equality here. This is the most simple one. But we have several questions. Because usually, sometimes, when the function is not L smooth, okay, then how do we determine the step size alpha? This happens sometimes. And even f is L smooth, but we do not know the value of the capital L. Sometimes it's not easy to know the exact value of this capital L. Then how do we choose the step size alpha, okay? In this class, we will propose the Armijol search to solve these two problems. To determine the step size, usually we need to consider 2 points. First, how do you calculate, okay? For example, you can choose a constant, or you can choose a initial step size. For example, you choose 1 and reduce it until it satisfies some conditions. This is the second point. When should you stop or when will your step size satisfy some stopping conditions? Usually this kind of stopping conditions can support your convergence analysis, okay? First, we will recall the analysis for the gradient method with a constant step size, okay? If we assume the objective function is L smooth with the ellipsis continuous of the gradient, okay, we will have this descent lemma we have proved in last class. If you do not know, you can go back to the last video. Okay, it says the fx plus 1 minus alpha fxk is less than the first term and plus, sorry, there is a square here, okay? There is a square here. It can be bounded by the first assumption and a second order term. Okay, next, if we consider the gradient descent method with constant step size, okay, we use this definition, we substitute xk plus 1 with this form, and then we can get this gradient descent lemma, okay, just use the gradient descent for the descent lemma. And then we get this one. And we have analysis this before. If we choose some alpha, for example, if we choose alpha is greater than 0 and less than or equals to 1 over L, we can have this inequality. Okay, we can have this inequality. And first, this means your next, the function value of your next point, okay, this is xk plus 1, is strictly less than the current point, okay, and even more, you can have an upper bound of your increment of your function value, okay, and then from this inequality, if we make a summation, okay, from k equals 0 to the capital T, then we can have this inequality. If we take the T approaches infinity, we will have some kind of convergence result such that at some point of your sequence, the gradient, the norm of your gradient will approach 0, okay, at some point of your sequence. Okay, so to get the convergence of gradient descent method with constant step size, the key point is this kind of condition, okay? We call it not only descent condition, we call it a sufficient descent condition, okay? Because it means the function value descent is decreasing, and which upper bound by these terms. Okay, so let's forget about how do we calculate the step size. First we think about what kind of condition we need, or what kind of inequality we need to guarantee the convergence without the L-smooth assumption, okay? So the easiest one is the descent condition. Sorry, it's a typo here. Descent condition, which means your function value decrease. Obviously, this cannot guarantee your convergence, because imagine in each iteration, your function value just decrease a little bit, very, very small. Even you make a lot of even if you make a lot of iterations, but you cannot reach your stationary point or your minimum point. And then we consider this kind of sufficient descent condition, okay? This is somehow we write similar with the last one. Let's go back and recall this one. This is what we get for the constant step size, okay? With Lipschitz continuity, we have this. Okay, instead of using 1/2, okay, we give a constant, okay, sigma, where sigma could be 1 greater than 0 or less than 1, okay? And here we use alpha k because the constant may not be fixed in each iteration. So we guess if we have this kind of similar inequality, we call it a sufficient descent condition, perhaps we can have the convergence. Okay, next, we analysis on in another point of view. Okay, we define this univariate function phi alpha, okay, which equals to fxk plus alpha dk minus fxk, which measures the increment in each iteration of the function value. And this function, only the variable of this function is alpha, okay, it's in R1. And we also assume f is convex, okay, it's easier for us to analyze the convergence. Okay, so for example, our current point is here, okay, and this direction upwards is the gradient, and the inverse direction is the negative gradient. Okay, so if we want to decrease the function value, we should go along this direction, which is the negative gradient, okay? And we can see that if we go a little bit, then the function will decrease. And until this point, which is tangent to this ellipsoid, okay? Until this point, your function value will approach its minimum along this direction. And if you go further, a little bit more, your function value will increase. And until this point, you will arrive in the same level curve or the same level set, okay? So at this point, you have the same function value, which is corresponding to this point in the graph of phi alpha, okay? You see, in the beginning, when alpha equals 0, which is corresponding to this point, and when you increase the alpha, then your function, this increment will be negative, okay? It will be negative, It means the function decrease, and until some point, the increment is the largest one, which means the function reaches the minimum along this negative gradient direction. And then after this point, if you go further along this direction, your function value will increase, okay? And until this point, which are corresponding to the point here, okay? With this step size, you recover your function value. And from this point, if you go along the direction of negative gradient, your function value will increase, will be even greater than your than the point of xk. So this also means even if you choose a descent direction, here we choose a negative gradient. Sometimes we also call it a steepest descent, which means it decreases very fast. But if you choose a not a proper step size alpha, for example, if you choose alpha here, perhaps you will reach some point here. It will not decrease your function, but increase the function value. Okay, so from this, from the analysis here, we have some ideas to choose. The ideas how to choose the step size. Okay. Here we define this univariate function again, but here we choose the negative gradient. Okay, the direction is the negative gradient. Okay, and since it's a univariate function, we can calculate the derivative very easily respect to alpha. Okay, we have this. Okay, and we can see that the phi prime 0 is just the norm of gradient at xk square. Okay, let's go back to the graph of this function which measures the increment. Okay, we define this point alpha hat, which is the intersection of the graph of phi alpha with the x-axis. Okay, this point is alpha. Actually, at least we want the step size is between 0 and alpha hat. Okay, the reason is we need to satisfy the descent condition. Okay, we do not want the step size in this part. Okay, in this part, because at this part it means the function value will increase. Okay, so at least we have this interval. Okay, which guarantee the function value is non-increasing. But actually, we also do not want the step size around this alpha hat. Why? Because we can say around this alpha hat, for example, if you choose a step size here, which corresponding to the increment is here. If you choose a step size here, very close or nearby the alpha hat, which means your function value doesn't decrease a lot. So somehow, we do not want the tail of this graph. We do not want the tail of this curve. Okay? So what we do? We draw a line, okay, a line here, okay, with the slope equals to the negative sigma times the norm of the gradient at point xk square. Where did we get this line? We get from this one, okay? We have a tangent line, which, tangent with this curve at the point 0, which has a slope equal to this one, where the calculation is here. But we want the point below some lines which has a higher slope, okay? So we times a sigma which is greater than 0 but less than 1. So we have a line here with a higher slope. So we want the step size which belongs to this line. So this gives this inequality, okay? We want this univariate function which is less than this part. Actually, what does this part mean? This part means, the right hand side of this inequality represent this line, okay, with the slope of the sigma, negative sigma times the norm of the gradient fxk square. Okay, we want this function is less than, or we want the graph of this function is below this line. So we have this inequality, okay, and we recall the definition of this phi alpha, okay? The phi alpha is just the measure of the increment of the function value. Then we substitute this phi alpha with the definition in the last slide, okay? We submit the alpha with this, with the definition here. And then we get this one. This is exactly what we have mentioned previous. Okay, we just go back a little bit. We can see here, instead of requiring the descent condition to guarantee the convergence, we want some sufficient descent condition, okay? We want something like this. And this is exactly what we guess from the condition for the constant step size, okay? Let's go back a little bit. This is the analysis for the gradient descent method with constant step size. We have this one. This is just from the descent lemma. Okay, but we cannot use descent lemma today because we do not have assumption of Lipschitz continuity. We do not have the Lipschitz continuity of the gradient. But we still want to get something like this because this we know can guarantee the convergence of the norm of the gradient. So we guess we want something like this inequality, which called sufficient descent condition. And finally we get it. We get this one, okay, from this inequality. And this inequality has a very good geometric interpretation, which has been showed here, which means we just accept the step size of this part, which means we just accept the graph of this phi alpha, which is below this line, and with the slope of this term, okay? So we have this inequality, and then we substitute of this phi alpha by the definition in the last slide. Then we have this one, where the sigma is between 0 and 1. Okay, this is what we call the sufficient descent condition or Amijo condition. Okay, Amijo condition. Of course, you can also use any descent direction. Because here we use the negative gradient as a direction vector, okay? But actually you can use any direction which is a descent, okay? So if you use any descent, you have this inequality. Of course, the sigma also belongs to 0 and 1. Okay, so we get what we want, the Amijo condition. Okay, this two Amijo condition. But the next question is, if we choose any alpha k satisfying the Amijo condition, can we get the convergence result? Like if we take if we let k approaches infinity, can we get at some point your gradient is approaching 0? Unfortunately, the answer is not. If we just use the Amijo condition, or if you choose any step size which satisfies the Amijo condition. The reason why is the Amijo condition accepts very small step size. Let's go back to this graph again. Okay, so we analysis. The Amijo condition accept the step size in this part, okay? In this part, belong this line segment from here to here. But since you accept this part with very small step size, okay? But this small step size will gives you only very small descent, very small amount of descent of your objective function. So this is a problem. So actually, in the practical computation, to guarantee the convergence with the Amijo condition, we implement this kind of backtracking approach, okay? Which means usually you can choose an initial alpha. For example, you choose the alpha equals to 1, and then you check whether it satisfies your Amijo condition. If it doesn't satisfy, then you repeat it. You times some beta, which is constant, but between 0 and 1, okay? Then your alpha will decrease, become smaller. And then you check this inequality. If it is not satisfied, you do it again until you get the largest alpha, which satisfies this inequality, okay? Actually, here in these slides, we call the backtracking approach and together with the Armijol condition, we call it Armijol length search, okay? So if you only use Armijol condition, you will not get the convergence result, but with this kind of backtracking, you can get at least the convergence of the norm of the gradient, okay? Maybe not the convergence of your iterates, but you can get the convergence of your gradient. Okay, so this is the algorithms which implements the Armijol length search with a gradient descent, okay? So first you choose alpha x0 belongs to the Rn, and then you in each iteration, first we choose the decay, the direction vector is a negative gradient, and then after you determine the direction, then you need to determine the step size. How do you need to determine the step size? You use backtracking, okay? You check, you try alpha. If it doesn't work, you try beta times alpha until this inequality satisfies. As long as this inequality satisfies, you stop and you go to the next point by this scheme, okay? This is what we call gradient descent with Armijol length search. And actually, this converges, this algorithm converges. Okay, so before we go to analysis of the convergence, first we prove the Armijol condition is well defined, okay? Be careful. It's not Armijol length search, it's Armijol condition is well defined, which means in each iteration, you will finally find at least one step size or some step size which satisfies your Armijol condition, okay? Here, we only assume that f is continuously differentiable at point xk, okay? And the decay is a descent direction. One point. In the convergence analysis, actually we use a more general setting, okay? We just assume that decay is descent direction. Of course, we know that the negative gradient is descent direction, but we prove something more general, okay? So you have a continuously differentiable function, and then a descent direction, then Armijol condition will be satisfied with small enough alpha. The proof is simple. We just use the first order approximation, okay? First order approximation, and we add some term and minus some terms here, okay? And then we put this term together and alpha outside, okay? And this term and this is less than equals to this term, just because this inequality, okay? Because this term is a small enough, and we assume that the decay is descent direction. So this inner product is strictly less than 0. So we can assume this part is less than 1 minus sigma over 2 times the inner product of the gradient and decay is less than 0. Okay, so we use this inequality in the last here in the analysis here. Then we can get for small enough step size. Okay, if alpha is small enough, this inequality will hold, and this inequality also holds. Will also hold. Then we can get this well-defined lemma, which says for small enough alpha, the Armijol condition will be satisfied if your f is continuously differentiable at xk and decay is descending direction. Okay, next we will go to the convergence. Be careful, the convergence here is about the norm of the gradient, not the xk. So we assume that xk is generated by this scheme, okay? And we assume that this decay is descent direction. And alpha k is chosen by Armijol length search. Be careful. Armijol length search means you need the backtracking with an initial step size. Okay, you backtracking. If it doesn't satisfy your Armijol condition, you times the beta, decrease it and check again. Okay, until the largest alpha k satisfies your Armijol condition. So Armijol length search means two things: the backtracking and the Armijol condition. Then every limit point of xk is a stationary point. Okay, let's go to the analysis of the convergence. Okay, first we consider the armature length search, and the x bar is the limit point of the xk. Be careful. The armature length search is stronger than the descent. The armature condition is stronger than the descent condition. Okay, so which means your xk is monotonically non-increasing. Okay, so the this fxk. Sorry, here is the fxk. Okay. So your fxk is monotonically non-increasing. So your fxk, the sequence, either converges to a finite value or diverges to negative infinity. Okay. Okay, but we assume that f is continuous. Okay, if f is continuous, then fx bar is also a limit of the fx of the sequence fxk. So the whole sequence converges not to the infinity but to fx bar. So we have xk minus fxk plus 1 approaches 0. Okay, this comes from the continuity of the objective function. Okay. Sorry, let me check. Sorry, we should assume there is something missing here. It's assumption of the objective function f. Okay. We need to assume that f is differentiable. Okay, it's differentiable at xk. Or we need to assume that x is differentiable in the whole space. Then we can get the continuity here. Okay, sorry about the missing of the assumption of continuity. Okay, so we have this, because of the continuity of f, we have this fxk minus fxk plus 1 approaches 0. Okay, then we use the definition of armature length search. Actually, we use the definition of armature condition. So we can get this here. Okay, we can get this armature condition. Sorry, there is xk here. So we know that the right-hand side of this inequality will approach 0. This part will approach 0. And remember that your decay is a descent direction, and the sigma is a constant between 0 and 1. Then we can say that the alpha k approaches 0 with some subsequence. Okay, so here we assume that xkj is a subsequence of xk such that this xkj approaches x bar, which is a limit point of xk, and we assume to arrive at a contradiction. Okay, we will assume that x bar is not a stationary point. Since decay is a direction, descent direction, we have analysis in the last slide. Then we have this alpha kj approaches 0. Okay, this subsequence of the step size approaches 0. And then by the armature length search, okay, because your armature length search is always just the biggest alpha which satisfies your armature condition, and together with this alpha kj approaches 0, we can find some index k bar which is greater than 0, such that for any kj is greater than k bar, this inverse inequality holds. Okay, this is not the armature condition. It's the inverse of armature condition. This inequality means after the k bar, okay, after some iterations, when you are doing armature length search, or when you are doing the backtracking, at least you need to try once before you succeed, or before the inequality succeeds. Okay, succeed. So this means at least you need to try once beta times alpha. Okay, so this is a key point. And okay, so since the decay is bounded, okay, then we take the subsequence of dkj. Yeah, because of the difficulty of a representation here, actually we need to choose another subsequence of the kj, okay? The subsequence of the subsequence. So we just use the kj here, okay? But you need to remember we choose a subsequence again, but it doesn't matter. It will not impact the proof. So we choose another sequence, subsequence, such that this dkj approaches some d bar, okay? Actually, this assumption of the boundedness of the searching direction is not very restrictive. For example, if you imagine if you choose a negative gradient as a direction, okay, it is always bounded. Okay, if it converges, it is always bounded. So we also assume that dk is bounded. Dk is bounded. So then we take a subsequence of the dkj such that this dkj approaches the d bar. And then we define this alpha kj bar just equals to this alpha kj over beta, okay? This part we define as the alpha kj bar, okay? So we have the same inequality but with the alpha kj bar, and we divided divided by alpha kj bar both sides, okay? So we get this inequality holds for any kj which is greater than the k bar. Actually, we remember that we take 2 times of the subsequence here, but we still use the kj to represent the subsequence, okay? And then we use the mean value theorem, okay? So we get this negative gradient xkj plus, okay, this alpha kj tilde is just some value between 0 and alpha kj bar, okay? So this is just the mean value, which also satisfies for any kj is greater than k bar, okay? And then we take the limit, okay? So left side we have this, because we already got that this alpha kj approaches 0, so this is just the xkj approaches its limit, so it's x bar, okay? And this dkj approaches d bar, okay? It's the same on the right hand side of this inequality, so we got this one, okay? And then since we know that sigma is greater than 0 and less than 1, we get that, sorry, there should be a gradient, okay? The inner product of the gradient of xx bar times d bar is greater than 0, okay? Is greater than 0. And this we get and here we get the contradiction, okay? We get the contradiction here, which shows that the x bar is a stationary point. Okay, so let's go back to here. Okay, so this algorithm said if we use this scheme, okay, with dk is a gradient descent and alpha k choose by immediate length search, then we can have that every point is a stationary point. But we need some assumptions, okay? So first, f is differentiable in the whole space. So it makes your gradient descent method or any method, any descent method makes sense, okay? And then we also assume that this dk is bounded, okay? This dk is bounded. And then we can have the convergence. We can have the convergence. And actually, we can get even more the convergence of the sequence. Here, if we assume f is convex and differentiable on the whole space, okay, with continuous derivative, and we suppose xk is generated by the gradient descent method, okay, with the immediate length search. For example, you choose the direction is the gradient descent, there is a negative gradient, and then you use the immediate length search to determine the step size. Then the whole sequence will converge to a solution of this unconstrained minimization problem, which is the minimization of the objective function f. Actually, you can check the preliminary result, or as far as I know, the result about this this convergence has been proposed by this paper, okay? It's by Professor Yusam, Zweiter, and Mauricio Regina in 1995. Of course, you can find it in some standard textbook, like the book by Professor Solodov, the Optimização Volume 2, which you can find the proof, but in Rn, in the finite dimension space, okay? But the analysis in this paper is in the Hilbert space, if I'm not wrong. And also I give you a reference about the Pertusecas. You can find the very good analysis about the convergence of Armigio lens search here in this nonlinear programming. Okay, this is what I'm going to talk about today. Actually, except constant step size and Armigio lens search, we can also use some other strategies which you can set up your step size in the beginning. For example, we can choose your alpha k such that which is okay, which is not summable, but square summable. Okay, this is called the diminishing step size. This is also another choice of the step size. What is the advantage of this step size? For example, you can choose your step size in advance. Alpha k equals to like 1 over k squared, okay? As long as you determine it in each iteration, you do not need to use the backtracking. Okay, backtracking is good, but sometimes if the computation of the function value is expensive, if you do a lot of backtracking, it makes your iteration very expensive. So if we can determine the step size before you go to your iteration, sometimes it can save the cost of computation, okay? But this kind of step size has a disadvantage such that the alpha k will approach 0, which is called the diminishing step size, okay? So in the next class, we will introduce a little bit more about line search, okay? We will introduce another kind of strategy, like it's called Wolf line search, and then we will introduce this kind of diminishing step size, okay? Actually, we have only introduced the Armigio lens search for the gradient descent method, okay, for solving unconstrained problems. But the Armigio search can be used in many other kind of methods. For example, it can be used for constraint optimization, like a projective gradient method. And it can also be used for the method for solving variational inequalities. But here, it's just one example of the implement of Armigio lens search. Okay, so that's all. Tá bom.